Well, as we been going through one-dimensional kinematics, we will kind of continue on. We had talked about acceleration and did some examples with that, and I believe this is where we left off, correct? And the acceleration tells us how fast the object is moving per second. Wrong with that. Does it always have to be per second? No. How something is moving per unit of time. So it can be kilometers per hour. Very odd, but could happen. Okay, those are some things. Acceleration tells us how much the velocity increases. That's wrong because the velocity could be decreasing. Yes, excellent. And therefore, both of the statements are kind of wrong with that. Those wrong statements. Now here's another thought-provoking question. If a negative acceleration is speeding up, or is it slowing down? Can a negative 7 meters per second be both speeding up and slowing down? Your answer is yes. The reason why we say that your answer is yes is a negative 7 meters per second if you're driving linearly on a car. That's a negative acceleration. Usually means you've hit the brakes or you've let off the gas, right? However, if you drop something vertically, it has a negative acceleration due to gravity. Gravity's acceleration is a negative 9.81 meters per second squared, or meters per second. And that's falling, and it's speeding up. How can we know that? Well, we can drop things onto somebody's head from different heights and see how much the hurt factor comes into play. So here is another part where what is the acceleration in this picture? The initial is negative 6 meters per second. Final, as we can see, the arrow is bigger. A negative 9 meters per second with a time interval of 2 seconds. If we do the math, we will see I have to get all my colors correct here. Initial minus the final minus a minus minus a minus, you end up with the plus there, so it would be a plus 9. So it'd be what, 1.5 meters per second. And therefore it would be speeding up. The math or the signs take care of themselves sometimes. Okay? Here, where would we say the detector is at? At the top or at the bottom of the ramp? They're at the bottom of the ramp. Okay, so you have to be careful. Sometimes that's going to kind of change how those numbers look. Where is the detector at? In our lab this week, that comes into play. Okay, where is the detector at? And some of those types of things. This is kind of your key. It is a key point. It is something that you probably should star, highlight, or make sure that you have the ability to reference it when you're looking at it. An object speeds up when its velocity and acceleration have the same direction. An object is slowing down when the velocity and acceleration have opposite directions. That is kind of your big thing with acceleration. It's important to make sure that we know, are they moving in the same direction? And that's why we always talk about draw it out. Even though you're like, well, I'm not a visual learner, draw it out so that you can at least kind of get what you're trying to envision in your brain. Even though you must say you're not a visual learner, you're envisioning it in your brain. You don't have to be a wonderful artist to draw physics problems usually. You have to be able to draw a dot, box, and an arrow for most physics stuff. And therefore, you should be able to at least, so okay, it's moving here, or maybe a line, okay? And if you're not good at drawing a straight line, well, good. Technology's helped us out so that even on like Notability, you can draw a line and it automatically straightens itself out. Or they have these things called straight edges or protractors that also help out a lot. Draw them out. It's going to be an important part of how you are wrapping your brain around what's going on. And when in doubt, draw it out. That's kind of the tagline. And look at the velocity and the acceleration. And if you can't find the acceleration, try to find it and see if that becomes a pertinent part of it. So we'll look at this for a moment. The accelerating directed upward and speeding up. Acceleration directed upward and slowing down. Acceleration directed downward and speeding up. Acceleration directed downward and slowing down. So take a moment and think about those things. What would be an example of acceleration directed upward and it is speeding up? Yes, real world examples help out wonderfully. Rocket. Again, rudimentary drawing. Speeding up and acceleration goes up. A little red right there. Some flames. Orange in those flames. All right. Accelerated, directed upward, and slowing down.
When it's going up?
A ball moving up a ramp. Accelerating upward. acceleration moving downward and slowing down would be a ball being tossed up into the air. Okay, that one would work for that one. It slows down as it gets to the top, right? But your acceleration is down. Acceleration directed downward and it's speeding up. That'd just be the ball coming back down, right?
So for the last ball one, would that be the second half? So once it reaches the top and then as it's coming down, specifically that section of the ball, or from release?
From release, so you're tossing it up into the air. Or it could be like the same thing, the ramp going up, the ramp, it is slowing down, but the acceleration is going the other way. So it's just riding on a ramp is really all it is. Okay. So the hardest one to come up with, acceleration directed upward and it's slowing down. Because anything that's on...
Wait, don't you... The last one, is that the ball coming?
Acceleration is always down.
Accelerating downwards and slowing down should be a choice.
So the parachute, try to get the right colors here.
For the parachute, you would be slowing down the most during like immediate release.
Immediate release of the parachute.
Yeah.
Because there is still an acceleration downwards, but there is that initial time where they go woo backwards. Or yeah, I have it drawn backwards, where the acceleration kicks them back. That initial deceleration. Yep, but they're still falling. So as we saw, it's not always super straightforward, is it? You have to think. And that's the part where people are like, but I don't want to think. Well, it's physics. We got to think. And it's not all, and here the other part is it's never, well, sometimes it's not going to be nice and cookie cutter. Here you go. It's not a cookie factory where we're just turning out super awesome things. It's messy sometimes. It's messy because when we took our pre-test, you saw nobody scored a 30 because you have some preconceived notions that are incorrect. And it's trying to get those out and coming to face with your preconceived notions. So, at times when we're looking at moving objects, sometimes it's hard to see the acceleration. That's why we like the ability to use graphs. So as this plays out over and over again, we can see object B probably has a nice constant or at least a initial a little bit more. It seems like it has a greater acceleration, but because it has a constant position time graph, okay, position time graph for B is B accelerating. Yeah, it's the initial, right, step on, but then it kind of just goes at the same rate across the board. Now C, if we look at its position time graph, looks like it starts the slowest, but eventually catches up to B because B isn't accelerating, but the green car does. Just not super awesome at hitting that accelerator. It's thinking about it a little bit. Where the blue car maybe didn't get a good jump, but definitely went zooming, accelerated through. Now, those are position time graphs. What would their velocity time graphs look like? Think about the slope of these lines to help you make that there. Then we would maybe even say, what would their acceleration time graph look like? So you would then take the slope of a slope, or the slope of the velocity time graph, and you're going to think to yourself, well, those would just be, might be just straight lines. You're right. They're just going to be a positive number or a negative number. So, such as this. How do you move your pencil to create this graph? Are you moving in a positive direction or a negative direction? Somebody smart will probably say, well, it depends on which direction you start drawing it. You start from the 0 point. Okay? The velocity time graph, you would start it from the 0 point and draw it. So the slope from this line would be positive or negative? It would be negative because it's moving in that direction. You just have that. So the acceleration time graph would just be a straight line somewhere on the negative. That would correspond to this graph here. Right? If we had numbers, we'd be able to do that. It bothers some people that we don't put numbers in some of these graphs, so we just say, hey, give us an idea of what do you think this looks like. And that is part of that. What do you think it looks like? And it might just be a straight line across. Now that we put numbers in here, you'd be able to make life a little bit easier, right? You're like, oh, thank God I don't have just unknowns and letters. Because nobody likes that in math class, but that's what you have to do sometimes. Now that we have some numbers here, we can definitely be like, okay, now I got this. Especially if we even add other numbers and say that that was 1 second. And say that would be 2 seconds. Right? Rise over run. Well, it's a dropping down to from 5 down to 0. Initial minus final minus the initial in 1 second. Have a -5 acceleration. So there you have kind of that idea. Sometimes it's nice to have numbers, but we still need to be able to think and just look at it and kind of know, oh, without even looking at the numbers, that's what this is doing.